Welcome to the video on the addition reactions of alkenes. In the previous chapter, we talked about doing elimination, removing a leaving group and a proton from adjacent carbons, creating that double bond. In this chapter, we're doing the opposite reaction. We are doing addition to a double bond. So addition is the opposite of elimination. We take a carbon-carbon pi bond and convert that into two new sigma bonds. And the chapter provides details on many different types of reactions. We can add a hydrogen and a halogen. We can add a hydrogen and an OH. We can add two hydrogens. We can add two halogens. We can add an OH and a halogen, and we can add two OHs. So we can do a bunch of different reactions with addition to this double bond. Many of the mechanisms are similar, but yet in this chapter, many of them are also unique, and they have special characteristics which set them apart from the rest. And so we will go through the mechanisms in all cases. Addition reactions in general begin because the pi bond, those pi electrons, are nucleophilic. And so they can react as a base and or as a nucleophile. And so that's where we get our reactivity, is that those pi bond electrons are reactive. If we look at addition versus elimination, we see that at low temperatures, addition is favored, where we add across the double bond in an addition fashion. Whereas at high temperatures, elimination is favored. And we can remember that from the previous chapter. Whenever we added heat, that usually implied that elimination was going to happen. It turns out that at low temperatures, enthalpy dominates, whereas at high temperatures, entropy dominates. And entropy is randomness, and so entropy dominates, and elimination is favored. The bottom line for this chapter is that we're going to use lower temperatures when we want to do an addition reaction. The first reaction we talk about when we're talking about addition is hydrohalogenation. So we are going to add HBr across a double bond. And again, low temperatures. We can use HCl, HBr, and HI for this reaction. What happens is the H adds to one of the carbons and the Br adds to the other carbon. And if we look at a mechanism of that reaction, it is a two-step mechanism. The nucleophilic pi electrons are going to reach out and form a new bond with the proton of the HBr. In return, the two electrons in that bond hop onto the Br to make Br minus. What that gives us is addition of the proton to this carbon right here, creating a carbocation here. And so that is our intermediate, is a carbocation. So following the proton transfer, we have that Br minus acts as our nucleophile, and it forms a new sigma bond with that carbocation, giving us this product right here. So this is a two-step process, proton transfer, followed by nucleophilic attack. If we look at the energy diagram for this mechanism, here is our alkene, here is our carbocation intermediate, and here is our final product. Overall, the reaction is endergonic. Here's the proton transfer step, which is the rate limiting step, and then nucleophilic attack is the second fast step. So there is some stereoselective nature of this mechanism, and here's what I'm talking about. So when we start with this alkene, we can have two different things happen. We can either have the H add to this carbon, or we can have the H add to this carbon. And so if it adds to the first carbon on the top, we end up with this carbocation intermediate, which I hope you can see right away is a secondary carbocation. If, however, the proton adds to this carbon right here, then we end up with this intermediate, and we end up with a tertiary carbocation. So I hope that you can immediately see that this reaction is going to be the one that prevails. That is going to be the major product. The reason that that is going to be the major product is because the most stable carbocation intermediate is formed. And a very famous scientist, Markovnikov, is the one that discovered that this is going to be the major product. And that we'll call Markovnikov product or Markovnikov addition. Now, obviously, these would both go on to form products, right, where the nucleophile attacks the carbocation to make our product in the two-step reaction. So another reason why the Markovnikov product is formed is because of the energy of the transition state. When the proton is coordinated with the more crowded carbon, like here, it's a higher energy transition state. Whereas if the proton is coordinated with the less hindered, or the one with the more H's, then we end up having a lower energy transition state, giving us a lower energy intermediate as well. Whenever we have hydrohalogenation, we may actually be creating a chirality center. And if we do form a chirality center from our alkene, then we actually get a racemic mixture, an equal mixture of the R and the S, because that carbocation intermediate is planar, and so our nucleophile in the second step can attack from either side. Here's our carbocation intermediate, planar with our empty p orbitals. And like I said, the nucleophile can attack from either side. And so that's why we get an equal mixture. Hydrohalogenation is regioselective for Markovnikov addition. In 1869, Markovnikov observed that proton atoms tend to add to the carbon that already has the most hydrogens. And then the halogen is generally installed at the more substituted carbon. If, however, you want non-Markovnikov addition of an HBr to your compound, in other words, you want the proton to go on the carbon with the most carbons and the halogen to go on the one with the most hydrogens, that would be anti-Markovnikov addition. And the way that we could pull that off is by putting it in the presence of peroxide. ROOR is peroxide. That is going to actually facilitate a radical reaction, which gives us the non or the anti-Markovnikov product. So if we look at the regioselectivity of hydrohalogenation, we have our alkene here. HBr by itself gives us the Markovnikov addition. HBr in the presence of peroxide is going to give us the anti-Markovnikov, or I call it non-Markovnikov. Because we have a carbocation intermediate, we can absolutely have rearrangements. Anytime you have a carbocation, you can have rearrangements. So in this case, we can have a 1,2 hydride shift that is going to move this secondary carbocation into this tertiary carbocation. Remember, rearrangements will only happen if we're going to a more stable carbocation, not to an equally stable carbocation, and certainly not to a less stable. When carbocation rearrangements can occur, they will, just like carbocations we talked about in SN1 and E1. We will get some of the product before the rearrangement, but our major product is going to be the one with the rearrangement. So I'd like you to take just a second and see if you can draw the products of the following two reactions. We'll talk about these two reactions in class. There you have it, addition to an alkene, hydrohalogenation. Woohoo!